Hello everyone, thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Soil Pressures, and it is going to provide you fundamentals of stress transformation and also failure theories. I am going to give you an overview of what I am covering today's video. First at all, it is a bit of background to the topic, and then focus on the stress transformation and the failure theories, before wrapping up with conclusions. Okay, engineered structures are often used to control the positioning of soil or granular materials. To understand how soil or granular materials generate pressures on their containers, consider a box filled with wooden cylinders. Collectively, the cylinders produce a downward force on the bottom of the container that is equal to their weight W. It turns out that the wood cylinders push against the sides of their container. If we stop pushing them together with our hands, nothing stops them from just pushing each other out sideways. At a short distance down, both the vertical and horizontal pressures are small. At progressively greater depths, both pressure increase. Experiments show that for most materials, the ratio of the horizontal pressure to the vertical pressure is constant. We call this ratio the pressure coefficient, K. Thus, for granular materials, the vertical pressure at any depth is typically ρgh, while the horizontal pressure there is K rho gh. Clearly then, both the vertical and horizontal pressures increase linearly with depth. The shapes and packing of the particles in a granular material affect the contact angles between them. Those angles and the coefficient of friction between adjacent particles determine the magnitude of the outwards pressure pH that is generated, and so they affect the value of K. If these ellipsoidal candies laid mostly horizontally, they would produce less horizontal force than if they were randomly placed or if they were spherical. Also, if the surfaces of either kind of candy became sticky, the lateral force would be reduced. We can observe the pressures produced by granular materials by using this apparatus. It consists of a rectangular chamber with windows attached to force gauges at 3 different depths along the side, and one window and force gauge at the bottom. The gauge readings allow us to determine the horizontal pressure at 3 elevations along the side of the chamber and the vertical pressure at its bottom. Using this information, we can determine the horizontal pressure distribution along the side of the chamber and the vertical pressure at its bottom. When the chamber is filled with marbles, an example of a granular material, the horizontal forces are 7, 14, and 19 Newton, and the downward force on the bottom window is 33 Newton. And it is easy to see that the corresponding horizontal pressures do indeed increase linearly with depth. Based on a straight line fit, the horizontal pressure at the bottom of the chamber would be 2.2 kPa. The measured vertical pressure there is 3.3 kPa. And dividing the horizontal bottom pressure by the vertical one gives a K of 0.67. Okay, now we move to the fundamentals of soil stress fields. We know that when we apply loads to an object, like this retaining wall, if we keep increasing the magnitude of the load, at some point the material will fail. But how can we predict when static failure will occur? What level do the stresses in the object need to reach for it to fail? First, we need to define what failure is. For soil materials, failure is usually considered to occur at fracture. They occur when the stress in the object reaches the ultimate strength for soil materials. In order to visualize soil stress fields, Mohr circle is a graphical method for easily determining the normal and shear stresses for different orientations of our stress element, without having to use the stress transformation equations. Let's see how Mohr circle is constructed. First, let's draw the horizontal and vertical axis. Normal stress is on the horizontal axis and shear stress is on the vertical axis. We will plot positive shear stresses in the downwards direction. Next, we plot the stress conditions corresponding to the x-phase of our stress element by plotting a point with coordinates sigma x, tau xy. Then we plot a point corresponding to the stress conditions on the y-phase by plotting a point with coordinates sigma y, tau xy. The line between these 2 points defines the diameter of our Mohr circle, which we can draw. Each point on the circle represents the normal and shear stresses for a certain orientation of our stress element. We can use Mohr circle to work out some interesting information. We can see visually that the maximum shear stress is equal to the radius of the circle, which we can easily determine either approximately by measuring the distance on paper, or exactly by using the equation for the radius of a circle. We can also determine the principal stresses by looking at where the circle crosses the horizontal axis, as the shear stress is 0 at these locations. The principal stresses can be calculated by taking the x-coordinate of the center of the circle and adding the circle radius. We can also use trigonometry to calculate angles on Mohr circle. For example, we can calculate the angle theta p between our original stress element and the principal planes. An important thing to note is that angles in Mohr circle are doubled compared to the angle we rotate our stress element by. This is why we use the 2 theta notation on Mohr circle. Theta is the angle we rotate our stress element by, and 2 theta is the corresponding angle on Mohr circle. Coulomb-Mohr theory is a failure theory often used for soil materials. It considers failure to be sensitive to hydrostatic stresses and captures the difference between tensile and compressive ultimate strength. The easiest way to define this theory is using Mohr circle. We start by drawing the Mohr circles corresponding to failure in the uniaxial tensile and compressive tests. By drawing lines tangent to both circles, we create a failure envelope. The angle is the soil internal friction, and the intercept on the y-axis is the soil cohesion. Coulomb-Mohr theory states that a material will fail for a stress state with a Mohr circle that reaches this envelope. The Triskar yield criterion is actually a special case of the Coulomb-Mohr failure theory, where we have the same material properties in tension and in compression. In general, soil lateral stress is a range between active and passive earth pressures. In this figure, the x-axis represents the horizontal displacement U of a point at a depth on a retaining wall, and the y-axis is the earth pressure P at the point. The curved solid line represents the relationship between the total earth pressure Pu and the displacement U. The leveled solid line represents the earth pressure at rest PO, which will remain unchanged with the variation of the displacement of the point. When the displacement reaches UA, then it induces the active earth pressure PA at the point. When the displacement reaches UP, then it induces the passive earth pressure PP at the point. From conclusions, what we learned: Mohr-Coulomb theory is a mathematical model describing the response of soil materials to shear stress and normal stress. In geotechnical engineering, it is used to define shear strength of soils and rocks at different effective stresses. The range of lateral earth pressures is between active and passive soil pressures. Okay, Thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching